In this lab, we have a lot of material that we need to cover. So what I'm going to do is going to go over some functional reading first, and then I'm going to go over some pre-lab reading as well. So this is just to get us ready for the lab. There are going to be timestamps in the description below the like button, and hopefully on the time lapse of this video or time whatever of this video, so you can scrub through that and see the specific parts that you need. But for me, I'm going to go over this just to make sure everything is clear. So first we have our PDF here. It's functional debugging. So we have embedded systems and applications. It's functional debugging using the SysTick Timer, and this is some new material that we've just learned. Those notes are also in the description below the like button. But for preparation, we're going to need a launch pad. We're going to want to run Lab9's starter file on our simulation and on the real board. So we are going to want to do this, answer any questions that we might have. That'll also be in the timestamps. And then we're going to get onto the actual coding and the board and everything for it, because it's pretty cool. So what's the purpose of this? The purpose of this lab is to learn about time delays, arrays, and functional debug. The data we collect will be physical proof that the system operates within our specifications. So let's look at our system requirements. The starter project is the same as the C9 debugging example in the Texas software folder. It includes the connections to our automatic grader as well. So again, if you don't know how to open this, there is the first video, I believe, in the playlist, and that will show on how to open everything and download everything correctly if there's any troubles there. So first we make the LED flash at 10 Hertz. In other words, we're going to want it to run for 0.05 seconds. Time is equal to 1 over frequency, right? So if you have 1 divided by 10 Hertz, it's going to give you, what, 0.05 seconds. So that's how that's calculated. This is then going to turn off for that same amount of time, and then we'll see what happens from there. If we're still holding the switch, it's going to keep going. If not, nothing's going to happen. So secondly, we are going to make the LED flash if either switch 1 or switch 2 are pressed. So this means either PF4 or PF0 is 0. So remember, two switches, right? One is going to be PF4, one is PF0. So if they're pressed, because this board, we're using negative logic here, when it's pressed, it's 0. So in their code, it's going to have to deal with like a not. Then it's going to register, send current through, and our LED is going to flash. It's going to toggle. Third, we want to record our port F bits 4, 1, and 0 every time the input changes to the output. The output changes. So for example, if our system detects a change in either of the inputs, we want to record the bits. And if our system causes a change in PF1, we're going to record two port F bits 4, 1, and 0. So we're going to want to record these and keep them in our array. In order for the grading engine to see and grade our data, please leave the debugging array defined exactly as a starter project. So we're not going to be touching any of the predefined stuff as well. So let's look at our unsigned long data 50 right here. This is going to be our array. It's unsigned long. It's data as the name, and then we pass in 50, that's the size of it. The system will be graded on its ability to satisfy the following requirements. So if our PF4 and PF0 switches are not pressed, the PF1 output should be low, registers nothing. If either the switches are pressed, the output toggles at 10 Hertz, and then we have a plus minus 10% error. This is because we're going from an exact simulation to a real board, which does have some kind of wiggle room, some percentage in there. Information collected in the data array matches the I/O port F. We have 50 data points, and they're collected only on a change in input or change in output. Remember, it only goes up to 50. No additional elements in the array are equal, so it's going to be different. Now this is what we should kind of aim for our logic analyzer inside of our code to look like. So the logic analyzer output showing PF1 toggles at 10 Hertz whenever the PF0 or PF4 is low. So again, we have our logic analyzer, it's here. It's going to be inside of our Texas grader, and the logic analyzer outputting the output showing PF1, and PF1 is whatever we have as, again, our output. It toggles, so that's going to be this right here, at 10 Hertz, so this is about 10 Hertz, whenever the PF0 or the PF4 is pressed, and those two are our switches. So on this top part here, we have our switch. This next one right here is going to be our output, and this last one right here is going to be our other switch. So we can see the first switch is pressed here, it toggles, released, nothing happens. The next one is pressed down here, and then it toggles. So that's how the two would work. Now we're going to want to debug in our simulation. Everything here is pretty simple, just remember part D. Part D is important, okay? So we had to change this, and I was scratching my head for a little bit, but we should mask the port F data with 0x13. So keep in mind 0x13. We're going to come back to that later when we go into our code. So that's really it for this part right here. We're going to go over our pre-lab questions in a second, but that's after we go over pre-lab reading. We're just going to go over this document. It's also pretty short, and we're just going to go over some background information that'll help us answer these questions, and then we'll get on to the actual lab itself. So this is our required pre-lab reading. We're going to be prepared to answer some questions. Those were these pre-lab ones once we're done understanding this document. So in this lab, we're going to illustrate a formal method for testing. Because embedded systems are deployed in safety critical systems, we need to be rigorous in our methods that evaluate if the deployed system performs its tasks as required. You can think of it as like a Tesla autopilot. If that's going to be full self-driving, that is going to have to work almost all the time, basically 100%. Embedded systems not only need to arrive at the correct answer, they need to arrive at it at the correct time. We will introduce a simple hardware counter that we can use to measure the time. The testing method we will develop in this chapter will be to create a data logger to store when and what our system is doing. So the learning objectives for this is to understand the concept of minimal intrusive debug, learn how the SysTick counter works, and learn how to create a debugging dump. We want to understand that a formal method to verify program correctness, it exists, and we should learn that. We want to learn how to use the dump to collect debugging information in real time as well. These sections are more kind of compressed versions of the notes that are in the description below that like button. But first we're going over 9.1, and this is debugging in a minimally intrusive manner. So every programmer is faced with the need to debug. You're always, forever, you're going to have to debug no matter how good your code is. You do this to verify the correctness of your software. A debugging instrument is hardware or software used for the purpose of debugging. In this class, we are going to study hardware level probes, like the logic analyzer, oscilloscope, joint test action group, so JTAG. It's standardized in the IEEE language. Its interface, we have a software level tools, so like simulators, monitors, profiles, and manual tools like inspection and print statements. Non-intrusive is the characteristic or quality of a debugger that allows a software or hardware system to operate normally, as if the debugger did not exist. Intrusive is used as a measure of the degree of perturbation caused in system performance by the debugging instrument itself. For example, a print statement added to our source code is very intrusive because it significantly affects the real-time interaction of the hardware and software. A debugging instrumentation is classified as minimally intrusive if it has negligible effect on the system being debugged. In a real microcomputer system, breakpoints and single steps are intrusive because the real hardware continues to change while the software has stopped. When a program interacts with real-time events, the performance can be significantly altered when using the intrusive debugging tools. Other hand, we will learn later in this chapter about dumps with filters, monitors. So this is like without strategic information on LEDs or a LCD display. So again, we are going to learn about these debugging things without LEDs or LCDs, which are less intrusive. A logic analyzer passively monitors the activity of the software, and it's completely non-intrusive. So a logic analyzer is what we're going to be using, and it's pretty good. Next, we're going to move to our 9.2 SysTick Timer. So time is an important factor for embedded systems. The SysTick Timer is a simple mechanism we can use to measure and control time. It is a 24-bit timer such that the current counts down every bus cycle, after the current counts to 0, it's automatically reloaded with the reload value and continues to count. So imagine you have like 1,000 inside of our reload. This is going to go to our current. Our current is going to count down from 1,000 to 900, 800, and so on until it hits 0. Once it hits 0, it's going to get reloaded with whatever values in here, and it's going to do it again. We have this video on how our SysTick works. We can click it, and this is going to just give us a demonstration here. And so this is what some of the nets are based off of. This should be in the description below the like button. I'll try my best to remember to link that as well. SysTick is a simple counter that we can use to create time delays and generate periodic interrupts. The basics of a SysTick is a 24-bit down counter, so 24 bits here, and it's called current. It runs at the bus clock frequency. Table 9.1, which we're going to get to, shows the register definitions of our SysTick. There are 4 steps involved in the initialization of our SysTick timer. First, we're going to clear the enable bit. So this turns off SysTick during initialization. We start with it off. Second, we're going to set the reload register to the max value that we want it. Third, we want to write the NVIC st current R value to clear the counter. So we're then going to clear whatever is in our counter. And lastly, we write the desired mode to the control register, which is our NVIC st control R. The mode involves the CLK, clock SRC, and the in10 bits. We set the clock SRC bit specifically that the core clock will be used. We set the clock SRC to be 1, so the counter runs off the system clock, and in later labs we will set the in10 to enable interrupts. But for this example, we clear our in10, so interrupts are not going to be requested. We're not going to be using any interrupts here. We need to set the enable bit so that the counter is going to run. Once our initialization is complete, the timer starts to count down. The current is decremented once every bus cycle, which is what we talked about here. Current goes from, like, if it's 1,000, 900, and so on and so forth, but just one. So it go like 1,000, 999, 998, 997, and so on and so forth. So we have our addresses here, and we're count, clock, in10, enable, and the names for these. When the current value counts down from 1 to 0, our count flag is going to be set. On the next clock, if this is set, the current is loaded with the reload value. In this way, the SysTick counter is continuously decremented. If the reload value is n, then the SysTick counter operates at modulo n plus 1. So we have like n, n minus 1, n minus 2, we have like 1, 0, n, n minus 1. So in other words, it rolls over every n plus 1 counts. In this chapter, we set the reload to be the 0, x, 0, 0, and ff, ff, ff. So 8 or 6 f's, 8 different bits. So our current value is a simple indicator of what count is now. Noting what the count was at some point and then what it is now allows us to calculate the time that has elapsed. So we have a previous time and then we have the current time. We can compare them. And this is without activating the phase lock loop, which is the PLL. Our TM4C123 launchpad will run at 16 megahertz, meaning the SysTick counter decrements every 62.5 nanoseconds. Remember that time is just 1 over our frequency. So if we take our frequency, 16 megahertz, and mega is going to be 10 to the 6. So we do a 1 divided by a 16. This is going to give us 0.0625. Now the megahertz should be on the bottom with the 16, but we can just change this to be a 10 raised to the negative 6. If we flip the signs, we can do this, the units. So we're going to multiply that in to our calculator, and then we are going to get 6.25 times 10 to the negative 8. Now if we move this over 6.25 like how we have here, it's going to be times 10 to the negative 9, and we know a negative 9 is just nanoseconds. So that's how we would get that there. Simple calculation. If we activate the PLL to run the microcontroller at 80 megahertz, then the SysTick counter decrements every 12.5 nanoseconds. So again, we would just do 1 divided by, we could do parentheses, 80 times 10 to the 6th. That's another way we could do it. And then this is going to give us 1.28 times 10 to the negative 8. Just move it to the right one and we get 1 2.5 times 10 to the negative 9, which is the nanoseconds. So in general, if the period of the core bus clock is t, then the count flag will be set every n plus 1 times RT. Note that the NVIC STCTR-L-R control register will return the count flag in bit 16. The act of reading this register when the count flag is set will automatically clear it. So this is post-read. Also, writing any value into this register will reset the counter to 0, and it's going to clear our count flag as well, so we can remember this register as well. So this is important to write down, and also the 13 part that we had to change inside of here. Those are two important things so far. All of it's important, but those are going to be most significant in our code. We have our program 9.1, and it initializes the SysTick. To determine the time, one simply reads this register with the reload set to this right here, which is what we talked about. SysTick behaves like a clock. Every t time it counts down by 1. And when it reaches 0, the counter is reloaded with the register and it continues to count. So it's going to be continually reloaded like with this. We have our defines up here, and then we have our SysTick right here. So inside of our code, there's better explanation in the notes, but basically we're just setting our SysTick to 0. We're disabling it. And then we're going to set the maximum reload value that it can be. And then we're going to clear anything in our current. And then we are going to enable the SysTick with our core clock. And that's this last one. So that's going to be our program right there. This is also really important. Now we're going to be looking at using SysTick to determine our time. So program 9.2 shows how to measure the elapsed time between calls to our function. We can assume that the system calls the function action over and over again. The variable now is the time in 12.5 nanosecond units when the function has been called. The variable last is the time also in 12.5 nanoseconds when the function was called previously. To measure elapsed time, we perform a time subtraction. Since the SysTick counts down, we subtract last from now. So we're basically taking whatever time we had last and we're subtracting whatever the time is right now. Since the time is only 24 bits and the software variables are 32 bits, we AND with the register here to create a 24-bit difference. So we're basically getting whatever number we have, the small number we have, which is only 24 bits. We're ANDing this, and that's going to make it 32 bits. So as long as we AND it with this, it'll be the full 32 bits. And so this is what our code looks like. We have our unsigned long, last, and then the time elapsed. We have our void action right here. We're going to set now equal to this register. So basically we're setting what now is, which is what we declared right here, to whatever time it is now. Then we're going to find the elapsed time. The elapsed time, remember, it's the last time that we had minus the current time. We AND it with this to make up for the 24-bit difference, make it 32 bits. We're setting last equal to now. And this is our program, which uses the SysTick to measure our elapsed time. The first measurement will be wrong because there's no previous execution for which to measure. The system will be accurate as long as the time is less than 0.209 seconds. So basically what it's saying is that there is no last time, the original time, because we set last equal to now inside of here. So that's why it would be wrong. So precisely as long as the time is elapsed less than 2 raised to the 24th times 12.5 nanoseconds. This is similarly to the problem of using an analog clock to measure elapsed time. For example, you notice the clock says 10 when you go to sleep, and you notice this is 7 when you wake up. As long as you're sure you slept less than 12 hours, you can confidently say that you slept for 9 hours. Otherwise, you won't know. Because of like AM and PM, you won't know. Also, the days can change as well. Next, look at 9.4, which is functional debugging. There are going to be several debugging tools and instruments we can use. Many debuggers provide 3 stepping commands. So there's the step over, and step out commands to verify the working of the code line by line. A breakpoint is a mechanism to tag places in our software, which when executed will cause the software to stop. Now, normally we can break on any line of our program, but this method is not practical to test complex systems with thousands of lines of code. This is very, very intrusive, and it's a bad method of debugging, relatively bad for what we're doing. The use of print statements is popular. and an effective means for functional debugging. One difficulty with print statements is in embedded systems is a standard printer may not be available. Another problem with printing is that most embedded systems involve time-dependent interactions with its external environment. The print statement itself may be so slow that the debugging process itself causes the systems to fail, because remember, it's very time-specific. In this regard, the print statement is usually very intrusive, and we're not going to want this here either. So in this lab, we will be developing debugging methods that do have these limitations. Instrumentation. We're going to dump into an array with and without filtering. So to solve limitations, we're going to add a debugging instrument that dumps strategic information into an array at runtime. We can observe the contents of the array at a later time. One problem with dumps, though, is that they can generate a tremendous amount of information. If we suspect a certain situation is causing the error, we can add a filter to our instrument, and a filter is a software or hardware condition that must be true in order to place the data in our array. We're going to use some of that here. The process of functional debugging using the array dump is shown here, so hopefully I'll remember to include this, but it's actually going to be similar to this video. It's by Jonathan Balbo, and my professor uses this a lot. And then this one is another one as well. Hopefully I'll include both of these in the description below the like button with their actual tags like this right here telling what it is. We have an example program that we can look at as well. Now we look at our example program. In Lab C2, this is an example program in our Texas software folder. The goal is to create a system that toggle the light at 5 Hz. So this means that the red LED should be on for 0.1 seconds and off for 0.1 seconds. If we look at the LED with our eyes, it looks like it's running correctly. However, if we look at the signal on the oscilloscope or logic analyzer again, it still looks correct. But can we prove this? Well, in the debugging process, we will dump the values of PF1 in one array and the time difference into a second array. When we run our program, it reviews all 49 measurements of time differences with 1,599,996 bus cycles, which is 0.0999975 seconds. So it's close to our desired time of 0.1 seconds. So we can look at this code and see what it's doing. Our code is going to be quite similar to this. So the first data point, remember, is wrong. The other 49 are going to be correct, and that's just because we don't have a last time for this. We're first going to make our unsigned long time array and our unsigned long data array. We have our int main void, unsigned long I, we have our last, and we have our now. So we're passing all these in so we can use them. We want to initialize PF0 and PF4 to make them as inputs. This is not given to us, but we're going to do it in our code. We're calling our port F init. This will be in our code as well. So we are making our PF3 output, and the other one should be input. I don't think it mentions it here. We have our SysTick init, so it's initializing our SysTick, running at 16 megahertz. Our I is equal to 0, so this is the starting array of our index, and our last is equal to this register here. Now, while 1, so basically forever until we stop this, we are going to run this. First, we want to read the previous LED. So again, this reads the previous LED. We have our GPIO port F data R, so this reads whatever we had. Then we're going to want to toggle our LED here, and then we're going to output this to our LED. So again, we read whatever is in here to our LED, toggle our LED, and then we put the LED inside of here so we can output it. Now, if our I is less than 50, because we're going to be incrementing this here, we're going to set our now time equal to whatever time it is now, and then we're going to store into the time the last time minus our current time. So we have 24-bit time difference. We're going to make up for that by ANDing this. We have our data array, and we have our GPIO port F data, and then we have this register, it's port F data, and it's ANDed with the 0x02, which for our code we're going to want to make 0x13, which records our PF1. Last is now equal to our current time, I++, and then at the very end we are going to put our delay here. So this is instrumentation to record the 49 time differences. The debugging itself is shown in bold. Lastly, a black box recorder stores strategic debugging information in permanent memory, so that if an accident were to occur, we could recover the debugging information to see why the accident occurred. We can make a black box recorder out of programs in this section by storing the data in ROM. This is not intrusive. However, the white box method, which you can look up, is more intrusive, where we actually look into the program. We're now going to look at our Prelab questions. So the first is, what does it mean for a debugging instrument to be minimally intrusive? Well, minimally intrusive means that the debugging instrument has small and negligible effect on the system being debugged. If it is intrusive, it is going to interfere with our debugging. If a microcontroller is running at 50 megahertz, then the SysTick counter decrements every how many nanoseconds? Well, we're just converting from megahertz to time here, and time is just equal to 1 divided by the frequency. So doing this will yield us this answer. That's also how we would calculate number 3. If we change the bus clock to 50 megahertz, what is the longest elapsed time we could measure with program 9.2? And program 9.2 can be found in the notes linked below the like button, but it's going to be looking like this. Well, from this, we can use the following equation that we have down here, and we'll go more into that right now. We can see lower is going to be accurate as long as we have our time elapsed less than 2 raised to the 24 times this time here. 12.5 nanoseconds, because we're given 12.5 nanoseconds in here. So it's basically just putting time in here, whatever time we have. So our constant is 2 raised to the power of 24 times. We are given frequency. We need to convert this to time. Time is 1 over frequency. So that's what we would plug in here. It's 2 raised to the power of 24 times t. T is equal to 1 over f. This is going to give us 335.5 milliseconds. This can easily be converted to like 0.3 nanoseconds or something like that. When the SysTick counter, what event causes the count flag to be set? So with it, it's going to set whenever the counter decrements from 1 to 0. So we know our reload is going to have whatever number we give it, like 1,000. It's going to go to 900, 800, 765, and then all the way down till it hits 2, 1, and then 0. Once it hits 0, it's going to cause the count flag to be set. And that's how we would use the notes to answer this. Next, we're going to be looking at our coding and the board example. So starting out this lab, we have a lot of this commented out. So basically I commented everything that they gave us, and then later down below, I started coding it. So what they gave us is just basic introduction stuff. We have our preprocessor directive sections, so we're not changing anything inside of here. It's including the, I think, Texas grader and then something to do with our board. So those two are included. We have our global declaration section. So this is disabling and enabling our interrupts. That's specific here. And typically we would also include our other function prototypes that we're going to be using, because we have, remember, we have like delay, we have for the pins, we have those two at least. And so we would include these here, but what we're actually going to be doing is writing these out before we hit the main method. So we use them directly, and we don't just make new like instances of them. It's kind of a rough explanation. We have our subroutine section, so we're not writing anything in here. We have a description of this lab. We can go over it really quickly. So this Lab9 starter project is the same name as our C9 debugging example. So it's the example that we've gone over, just a few different changes, 3 specific. First, we are going to make the LED flash at 10 Hertz. In other words, it's going to turn off for 0.05 seconds and also turn on for 0.05 seconds. Secondly, this is going to happen, the LED is flashing if either the switch 1 or switch 2 is pressed. So this means the flash the LED if either PF4 or PF0 is 0. So we're going to make the LED flash basically. Third, and this is the new part, we want to record our port F bits, so 4, 1, and 0, every time the input changes or the output changes. So like for example, if our system detects a change in either the PF4 or PF0 input, we're going to record the bits, the port F bits 4, 1, and 0. Now if our system causes a change in PF1, we want to record the port F bits 4, 1, and 0 as well. Remember, PF4 and PF0 are just the 2 different switches. If both PF4 and PF0 switches are not pressed, the LED should be low, meaning nothing is on. If either the switches are pressed, the output toggles at 10 Hertz. Information is collected in the data array, and it matches the I/O on our port F. So remember, data array. 50 data points are collected only on a change in input or a change in the output. So this means that no adjacent elements in the array should be equal. Now, let's look at this. This is our port F that were given to us. We're activating our clock. we're allowing the time for the clock to start, unlocking the GPIO port F, allowing changes to be made for PF4. We do not need to unlock this. Other bits can't be unlocked. We want to disable the analog, so we're doing that here, and then it seems like we're disabling everything else. We're enabling pull-up resistors though on PF0 and PF4, and then we have our enable the digital I/O on our PF4. We have our SysTick right here, which we're also going to be using. We're putting this before our main function. That's why we don't need to list it in our function prototypes. We also have one for our delay right here. We have an unsigned long LED, so that I think will be useful. We'll come take a look at that again once we go into the actual code. So our first data point is wrong. Remember, that's because we don't have a current time that we're comparing it to. Only we don't have a last time, so that we're comparing it to. So when we have this last, we don't really have a last because we're just starting it now. So the first one is going to be incorrect. The other 49 will be correct though. So that's going to bring us to our code. We're going to have to change some stuff inside of here. So just take note of this, and we'll come down and change it. So now this is where our actual code is. We have our unsigned long switch 1 and switch 2. These are global variables. We're just registering our switches here. We're not changing our interrupts. Same instructions here, not changing anything inside of here. We're initializing our SysTick. Now we do have to change one thing inside of our delay because we want our delay to go every 0.05 seconds. And this goes 0.1 seconds. So we're basically just dividing our time by 2 to get it to be 0.05. Then we have this while time, and then we're just going through here. Now remember, first data point is wrong. Inside of here, we have our unsigned long time array, unsigned long data array, and then we have our int main void. So we have our unsigned long I, last, and now. These are variables that we're going to be using inside of here. We're activating the grader. We are initializing the port F, the PF1 to output, and that's going to be done up here. We just went over that. We have our SysTick init. It's initializing the SysTick, and it's running at 16 megahertz. We have our I equaling the 0, so this is just starting our array index. Lastly, we have the last set to our NVIC ST current R, and this is just our register for getting the, I think, current time. We are then going to enable interrupts, and then we can finally begin our while loop. So inside of here, we're initializing the ports, which are switch 1 and switch 2. We're using these two different ports. So we're using negative logic here, hence the nots. If switch 1 is not, or switch 2 is not pressed, but because it's negative logic, it's if they are pressed. We are going to read the previous LED. We're going to store an LED. We're going to toggle this LED, store an LED, and then output this LED using this register. Now, if I is less than 50, we are going to be inside of here. We are going to get our current time. So this is our now time, not the last time, right? And then we're just going to subtract them. Remember, for the 24-bit difference, we have to AND this 32 bits, storing it in time, the time array, and then we're going to do the same thing but for our data. Now we do have to change this though from 0x02 to 0x13, and that's just per the instructions. Last is equal to now, and then we increment our I so we can eventually stop having this data recorded. And then we have a delay. Remember, if our delay is to have the 0.05 seconds, once this happens, we're going to hit this delay, and then we're going to go through our while loop again. So every time we're going to want to do this delay. We could put this delay probably inside of here. That would work as well. Lastly, we have this else statement. Remember, when it's off, we don't do anything. So it's just going to be ANDed with a not red LED. So it should be off. Let's go into our settings. Make sure we're using the simulator. We can build our project. We can debug our project, press OK, and then we can click grade. We will see the logic analyzer. Whenever the switch 4, which is our one switch, is pressed, or our other switch is pressed, we are going to have it toggle, or whenever it's low. So we can see whenever it's low here, it's toggling. It's high here, it's high here, it's not toggling. This one toggles, it's going to, or this one is going to get pressed, it's going to toggle here. Neither is pressed, nothing happens here. And then both these are pressed, it gets toggled. So that's how that would work. Now we can make some modifications to this if we wanted to. Like, let's say we put our delay inside of here. So it delays right after it happens. That should work as well. So we will build our project. We'll go into our debug and we'll just test this out. Click grade. And we can see that this would work as well. Let's exit our debug and try something else. I'm not going to try this. This will definitely break it because it doesn't store it in the right space. Let's set our GPIO port F to just 0. What if we set it to 0? We end it with 0. We're going to build our project, go into our debug, go in here. And remember, it's flashing the red LED, by the way. You can see that it says red right here. And we still get 100. So the 0 would work as well. So those are just some modifications we could make to it if we wanted to. We have our LED ports here, and that's going to be it for the simulation of our lab. Next, we are going to be looking at the physical board itself. So I have my board here. I've already loaded the program onto the board, but if you have not already, we've done this in previous labs, we're just going to plug our board in. We're going to want to make sure it's switched on. It's in the debug mode. This light should come on. And then we are going to have our program. We just want to load it onto our board. If there's any problems, a simple way to fix it is just to clean our targets, build the targets, and then load it. You can go into our debug also to see more information, but this is just super simple. We're going to take the board, to get it to run, just press the reset button. And then from here, you can press either of these switches, and like the lab says, if we press one switch, the light will start flashing. Press the other switch, it'll start toggling as well. And then when we press neither, this light is not going to be on. So that's how you would do this lab, load it onto the board, and see the actual results from the simulation. And that is the conclusion of this Lab 9. More labs will be in the description, in the playlist below the like button.